when you say "Hey Siri" or "Okay Google" or Alexa, how does the device know that you're saying it, and how does it respond so quickly? This is happening on board, by the way. No cloud is required for it to process a keyword. So all of that is done using TinyML, and it's an interesting field if you want to build intelligent systems. Right, so we're gonna try to build one today, a wake word detector. In fact, I built one for my undergrad research project when I was trying to build a smart home assistant. So that's what we're gonna try to do today. So this is, I'm not really an expert, but I felt that I should share that with you as well. So the problem is that AI is expensive. As we all know, it requires GPUs, in some cases TPUs and accelerators, because the math involved in the computations around AI, it's quite heavy, right? There's matrix multiplication and all of that stuff, backward propagation, which requires finding gradients and all of those things. Those are very compute heavy processes, so they require GPUs, and their GPUs are quite good at that. But GPUs are expensive. There's a reason why Nvidia's market price is high up right now, because everybody is trying to build AI, and in doing so, you want to buy GPUs. And running these GPUs too, in turn, means that there's a lot of electricity used in running these GPUs in training your model. So that's also a cost, and it's time consuming. I'm pretty sure training a frontier model like GPT-4o, I'm sure it took a lot of time, right? So you may not have that time because you're just an ordinary person like me, right? So, and usually there's a high barrier to entry to research in AI. You need a PhD, There's no way a person like me would just magically end up at OpenAI. I would need to have a PhD, which I don't, right? So what about people like me and you? We still want to get our hands on AI. We want to be able to train our own models and deploy them in our applications. There's a field that actually allows us to do that, especially when it comes to cost, when you want to use it for small use cases, like running your AI models for anomaly detection, wake word detection, or even computer vision on tiny devices like a microcontroller or a single board computer. So tiny AI allows us to do that at a low cost in terms of time. Even you may not need a GPU at all, right? So one way to do it is this. We're gonna try to do TinyML and pretty much using TensorFlow Lite. It's not the only way to do it, but this is usually my go-to, right? You can also use ARM-based ways of doing it. I'm sure there's like a neural engine that they have. Well, yeah, experts know more about that than I do, and also there's you know people at Edge Impulse who are doing amazing work for you for streamlining the ML ops for you, so that you can pretty much quickly train your models and deploy them on your devices of choice, right? So we're gonna use TensorFlow Lite to train, or should I say convert, a normal model and deploy it on a tiny little device like a microcontroller or even a Raspberry Pi, to see if it behaves well, if it detects what we want it to detect. So this video really focuses on what's involved in training such models, right? And what's involved in also deploying them, right? So the overview really it's just a merge of two fields that are important today: embedded systems and machine learning. And when you merge them, the baby is TinyML. So TinyML is just that you train your model the way you usually train it. Let's say in Google Colab, you convert it to a TensorFlow Lite micro model and you deploy it on your microcontroller. So here you can see the diagram. There's a kit here. I'm sure UPenn is a course that teaches something about that. And also I took a course from Harvard online on edX, where you learn how to deploy these kind of models on an Arduino board. And that's pretty cool, right? And you can see the use cases in the Google Glasses, Amazon Alexa, and all these other things. You can use a gyroscope to measure think orientation and angular acceleration and all of those things, and find what do you find by that. What do you find? How can you train a model to predict or deduce meaning from all those things. So when your sensors giving the data to your computer, how can you do that at the edge without sending your data to cloud? So yeah, you train a model, you convert that model, you optimize it. There are many ways of doing so. There's pruning, which is pretty much removing either layers or even nodes within the neural network to ensure that it's small enough to run on a microcontroller, because mind you, microcontrollers have low resources, right? You're talking about maybe 2 megabytes of flash, or whatever it is that you are trying to work with. So you're not, compared to a GPU or something like that, that's nothing, right? And deploying that at the edge means that there's no more cloud. This reduces latency, by the way, and it improves privacy. So it's important for us to know this, right? And you do your inferences at the edge. So this is wake word detection. So this notebook, I used it during my undergrad research when I was building a smart home AI system on a Raspberry Pi. So I'm not gonna go over the entire code. I'm just gonna go over the things that I think are important, which are data pre-processing and training, and uh, conversion of the model to a TensorFlow Lite micro model, or TensorFlow Lite model. That is the micro part. We'll look at it later. So after the installation and importation of important modules and libraries, we get our data from Kaggle, right? And after getting our data, our Google speech command data commands data from Kaggle, then we unzip it, and then we check the examples that are in it. There's on, 0, yes, 3, and all these kind of words. And these are 1 second wave files. There's also background noise added, right? And then we can just try to see the examples. By the way, we can also just plot to see what they look like as wave files. So, for example, bird, it looks like this, 3 looks like this, left, or all these things. And it's pretty difficult to use that in its raw format as the input data for our model. It will be difficult for us to make any classifications on that, right? So what we're gonna do right now is convert these waveforms into spectrograms. Uh, and as you can see, on a waveform, you on the x-axis you have your time, and then on the y-axis you have your amplitude. So we can try to extract the frequencies of this waveform using the fast Fourier transform, or in this case, the short time Fourier transform, and TensorFlow allows us to do that quite easily. And when we use TensorFlow, we can compute and convert all these wave files into spectrogram. And to do that, I'm not gonna go over the data, right? For example, we have our example audio playbacks. We have bird. We have
3.
3. We have left,
Left.
right? And then we can plot the spectrogram after the conversion using the short time Fourier transform. And then when we plot it, it looks like this. For example, left, this is the waveform. When in the frequency domain, it looks like this, right? So this is feature extraction. It's very important because it allows us to use necessary information in our neural network so that it learns the key features that will enable the ways to do the classification for us, right? So there are other feature extraction methods that are used as well, like the MCC. I'm not going to go over that. There are experts who can tell you more about that, or maybe I can do that in another video. So for all the audios, pretty much we can get the spectrogram, and it looks like this. And these, if you can take a look like images, right? So we have pixels here. So which means we can now use a convolutional neural network to do this classification, and we can build one, a simple one at that, right? This is the convolunet that we're using. How many layers? Well, you can count them, right? So we have our input layer, we have conv 2D, our max pooling, our dropout, and our normal dense layers as well, right? So this is the architecture of the model that we're using. It looks like that. parameters, over 1.6 million parameters, right? And then we can also get the flow diagram of that model. Sorry, it looks like this, so that we can visualize what it looks like. So this is the model, the convolutional neural network that's going to do the detection for us. Then when we compile the model, optimizer is Adam, and then the loss function that we're using is the sparse categorical cross entropy. And then our metric, we're tracking our accuracy, and then I'm using third epochs here. So how many times are we going over the data? That's exactly 30 times. Then after training, we track our accuracy, see how it performs, right? We can see that the accuracy is about 87% and our validation accuracy around much. So if there's not much of a difference there, well, it's doing well, and it did some early stopping here at epoch 17. Don't worry about that. Then we save our model as an H5 model, and then we can convert it then. And then we load our model, and the same model that we saved, we load it, and then we convert, right? Where we build our converter object, and then we convert it to a TensorFlow Lite model. And then this model, the TensorFlow Lite model, the TF Lite model, we can then convert it further to a TensorFlow Lite micro model. This is when we are now only getting like an array of the hexadecimal numbers that represent the model. Then we can maybe deploy that on an Arduino that has the enough processing, like an Arduino Nano 33, NB33. Yeah, that one works. And that's it, right? So in the next video, we'll show that in action. We'll actually deploy the model and see how it performs.